Okay, so correction from Friday. There are 37 of you, and nobody corrected me until the end of class. Somebody asked me a question about this. I will try not to make mistakes, but in calculus, there's so many calculations that we need to do. Please correct me if you see that I'm doing something wrong or I make a simple mistake. So on Friday, when we did class example number 5, I forgot the 2. Okay, so obviously we got the wrong limit. You guys probably recorded -1/2 on your sheets. It's actually supposed to be -1. Okay, so there's the correction. Today, when I made your notes package for limits, I also forgot a page. So this is what we're going to be working on today. You can slip it in your note package or just keep it separately. So we'll start with this little sheet that I gave you today, and then we'll jump back into those little booklets I gave you about continuity. And that'll be the first half of today's lesson. So we're going to work on lesson 1.3, which is those absolute value and split piecewise kind of functions. How did the homework go? Okay. I will also be posting the homework solutions, like the work through solutions, but just keep in mind the textbook is really old. It's like 35 years old. So the solutions are very old looking as well. So I will post those on the Google Classroom, but they're not as nice as if we were to create our own solutions, but they are better than just the answers in the back of the book. So absolute value or piecewise or split. Okay, there's a lot of different names for these types of functions. We'll graph a few of them. But for now, we have the understanding of what a limit is, hopefully. Okay, so it's when a function approaches one number. We also know that with the definition of a limit, in order for it to exist without the plus and the minus, we have to have the left side matching the right side. That's most important, especially when we're talking about a split function, because we can have a graph that looks like this, right? And then we know it's got 2 sections, but it's discontinuous. And if I was asking for the limit right here at A, it would not exist because the left and the right are not approaching the exact same number. But if I had maybe a piecewise function that was maybe an absolute value and then a quadratic, and I had the left approaching the right, that type of function would have a limit exist at this value. Let's call it A. Okay, so that's what we mean by these split functions, is they have different parts to it. It might be a linear and a quadratic. We're going to get into some more complex ones that might be a log function, an exponential function, and a trig function. Okay, so all the different stuff that we've done in 10, 20, and 30. Specifically for the beginning today, notice how here we have a limit as x is approaching A. And then over here in our notation, we have x is less than b or x is greater than or equal to b. When we did our piecewise functions in 20-1, most of the time we made the top one have less than or equal to or greater than or equal to. Now it doesn't matter. With our split functions, we can have the whole thing not equal to anything if we don't want to. So that's what I mean about this symbol underneath. It can change based on the type of function that they give us. Okay. One thing to keep in mind, b in here is called our breaking point. So this would be B if I wanted to know. It's where the graph potentially might break, okay? So B is our break point of the function, and at this point, the graph may be discontinuous or broken. So that's why we call it the break point. There are 2 ways to find limits of piecewise functions. The first one, as you have on your notes, is when our x is approaching and the A value is the same as our breaking point. Okay, so this is the first when A is actually equal to B. So we have an example here. We have the limit as x is approaching 0 for the function f of x. The function f of x is defined by -1, so a constant function at -1 for all x values less than 0. It is also defined as a linear function x plus 1 when x is greater than or equal to 0. So notice here, I'm approaching 0 and my breaking point is also 0. Okay, so when those two numbers match, Now what we're going to do is we're going to try to find the limit. So notice how we have to the left of 0, and here this is to the right of 0. So on your notes package that I gave you, the flow chart on the front was what we were working with yesterday or Friday. If you turn to the back page, the second flow chart is what we're going to be doing today. So our double or split functions. So you can see on the back of that flow chart, the first box says, is A equal to B? Is the limit being taken as x approaches the breakpoint of the function? If it is, which is our example it is, what we're going to do is we're going to look at the left-hand limit and the right-hand limit. And for this to exist, that left-hand limit and right-hand limit have to equal each other. So notice how I labeled this one is our left. It's not always going to be the top one is the left and the bottom one is right. They can switch. Okay, so what I mean by the left and the right, well, anything less than 0 is the left side of 0. Anything greater than or equal to 0 is to the right side. So that's how I know it's the left or the right. So when looking at my left-hand limit, I have the limit as x approaches with that little negative on the top representing that it's the left side. Now, I choose which section is the left side, so I'm going to have -1. Now, if I were to think of that graphically, what it will look like, which we'll do in a second, the limit of a constant is a constant because I can't plug in 0. And I know that graphically, less than 0, right here at -1, it's going to look like this. So from that left side, it's approaching -1. So this limit is -1, okay? So the limit of a constant is that constant. Now the right-hand limit is the limit as x approaches 0 from the right, so we put that little plus. And this time, I'm going to choose the part that is the right side, so the x plus 1. Okay, so that is the right side of 0, which is the x plus 1 gets me that part of it. And this, I plug the number in, and I get 1. So does this limit exist? No. So the limit as x approaches 0 of my function x does not exist. Okay, because 1 is approaching -1, 1 is approaching +1. Again, if I were to graph the second one, it looks like this. This graph is discontinuous at 0. There is an actual break in the graph at that point. And the limit doesn't exist because the left doesn't match the right. Okay, so that's how we approach these types of limits. Let's do one more where a is equal to b. So you have the limit there as x squared minus 5 when x is less than or equal to 3, and x plus 1 when x is greater than 3. So it's set up the same. Remember, these two might not always be left and then right. It could go right side and left side. It doesn't matter. And we can have more than just one section. This, because it's less than 3, it represents the left-hand side. Okay? This one being greater than 3 is the right-hand side. Okay, so good to identify which one's the left and which one's the right. Notice again, our breaking point is equal to the value that we're approaching with x in our limit. So we're going to take the left-hand limit, which is going to be the x squared minus 5. And remember, we're plugging in our 3. And we get a value of 4. I do the same thing as our last example, and we now have to take the right side of that limit. which is x plus 1. And I plug in my 3, and I get a 4. So the left hand matches the right hand. We can say left hand limit equals right hand limit. So the limit of this function as x approaches 3 has a value of 4. And so this one does exist. Okay, so you have another example there for you to try. So go ahead and try as x approaches -1. Determine which one's the left side, which one's the right side, and see if they're equal to each other. Okay, so you should have got a limit of 1. Okay, so our left-hand limit, we plug in our -1 into our x plus 2 and get 1. Our right-hand limit is x squared. -1 squared is 1. Good? Pretty easy, this limit stuff. Okay, so let's switch it up. What happens with case 2 when a is not equal to b? It's actually easier than when a is equal to b, because now we just have to decide you just have to pick the one side where a actually falls. So when a is not equal to b, we only have to look at one of them. Okay, so if I look at this example that you guys have, once again, we have our a value is 3, but our b value is 0. So they're not equal to the same number. So if I were to look at my split function, is it the top or the bottom that's going to give me an a value of 3? Where does a fall? Obviously in this one. So I don't care about the -1. All I care about is that bottom one. So to find the limit as x approaches 3, I'm just going to use x plus 1 because that a value falls in this function. It's greater than or equal to 0, so that's the one I want to use. I plug it in, and I get a value of 4, and we're done. Okay, so even though that top and the bottom might approach different values, it doesn't matter for this one. And if I were to graph this one, so this one I want to graph or the next one? maybe neither one. We'll skip the graph. Let's go to this one. Okay, so you have the limit as x approaches 1 of f of x, where f of x is x squared minus 5 and x plus 1. So again, my a value is 1, so that is going to be in the top function. Less than 3, 1 is less than 3, so the limit as x approaches 1, I don't need the positive or the negative because we're not taking it to the left and the right side of 1. We get x squared minus 5. We plug in our number, and we get negative 4, and that's my limit. Okay, so you have 2 there to try. So we have the first one, we'll call it A, where the limit is approaching negative 1, and B when x is approaching negative 5. So go ahead and try those 2. Okay, so for the first one, you should have got that the limit does not exist. So that a value equals that b value. The first one we get a value of 3. The second one we got a value of 0. So this one does not exist because the left and the right hand don't approach the same value. That is the break in our graph. Part B, as we approach negative 5, we only need to use the bottom, which is our linear function x plus 1, which is negative 1, or less than negative 1, and we get negative 4. Any questions with this? Okay, so the second part is a little bit trickier because you have to come up with your split function or your piecewise function. So that's when we have absolute value. Okay, so the next one, part 2 that you can see there is when we have absolute values, we're going to create this type of system. Okay, so as you can see for your notes, we have our absolute value function here. Remember when we always split it up, we would have the positive one, and then this is the negative one. Okay, so if let's say this is my graph, when I put this x minus a into absolute value, oh, this is a plus, so let me move this. Okay, so when we learned piecewise, we knew that this part was that positive one when a was greater than or equal to 0, or x was greater than or equal to a, sorry. Okay, and then we had the second part, which was down here, and this section was less than. Okay, so it's a simple example. This one's linear. We're going to get into more complex. We're going to do rational, because what this graph actually looks like, remember, is this. But I always like to think of it as if there was an absolute value. Where was your graph above the x-axis and where was it below? Okay, notice here we are setting it as x plus a is greater than or equal to 0, but then we simplify it. So this is how we want to properly write it. So whatever you have in that absolute value, that breaking point, okay, that's where we put it and solve for it. So we have the x plus a. Remember, this is what was in the absolute value. That's also really important. Okay, this is what was in the absolute value. So when finding out, we have to rewrite it this way. Okay, so we don't just like plug in our numbers and take a limit of x plus a in absolute value. You have to write it as your split function first and then evaluate it. Okay, a good heads up for your exam. So a little bit more complicated than just x minus 10. The other thing is there's a tricky thing with this one, with our breaking point, because notice where our x-intercept for just our absolute value would be positive 10. But what happens when I plug in a positive 10 here? It also gives me 0, which is a non-permissible value. So in this situation, in our piecewise, we can't ever have less than or equal to 10. We can just have less than or greater than. You'll see when we write it. Okay, so the first part is writing this limit without our absolute value. So we have x minus 10 in our absolute value, x minus 10. We're going to rewrite this. So the first is when we take it out as positive. So I'm just going to write it as x minus 10 over my x minus 10. And we will simplify it in a second. The second one, we take it out with a negative in front of that absolute value. Okay, so we have our positive one, we have our negative one. Then we say if, for this one, our point is going to be when x minus 10, I have no idea what's going on with this. That's an x minus 10 is greater than, and this is what I mean. This is something that I even make mistake. I can't have this equal to 0 because it's a non-permissible value. So this is just going to be, let's see if it works, greater than greater than 0. Okay, we'll simplify it in a second. And then we have the second one, if x minus 10 is less than 0. Okay, we're going to rewrite this because it does simplify. What happens when I go x minus 10 divided by x minus 10? What does it equal? Just equals 1. And then I'm going to simplify this by moving the 10 to the other side. So my upper, my positive 1, is going to equal positive 1 if x is greater than 10. This one is going to be negative 1 if x is less than 10. Okay, notice my breaking point is the same value as my a. So my a is now equal to my b. So I do my left hand limit and my right hand limit. Even though we can already see it's not going to be equal because one's going to be 1 and one's going to be negative 1, I still have to show it. So I'm going to have the limit as x approaches 10 from the left, which is going to be negative 1. And then the second one, the limit as x approaches 10 from the right side, that's the upper one, so that's positive 1. So equals 1. They're not equal to each other. So this limit does not exist. The left hand did not match the right hand. Is that a lot of work to show that the limit doesn't exist? Yes, but that is the whole point of calculus, is we're proving all of this stuff. Again, like I said, be very careful that you didn't make these equal to at any point, because it was also a non-permissible value. What else do you guys have? Okay, so then you have that bottom one where you have x minus 10 over x minus 10 as x approaches 4. Okay, sorry, and this limit, that one we just did was where it didn't have a negative here. This limit does exist. So if we're just looking at one side of it, this we know is +1 and -1. So if I'm just asking for this side of it, I just need this. So this one does exist because it's just one side. Okay, so a question might ask for just half of the limit, which is okay, that does exist. Okay, so when we have the limit as x approaches 4, it's kind of the same idea as what we just did, but remember the rules are still the same as they have been. When we have a +4, all we're going to do is plug the number in and see what we get. Okay, so it's still going to be the left side. So if I wanted to write it, all of these, we still have that function. This is greater than 10. Okay, so I'm still going to be using the side that has 4 included. So that limit would equal -1. But if I just forgot to write it and I wanted to evaluate this, if I plug in 4 into my actual function, I get the absolute value of -6 over -6, which is +6 over -6, which is still -1. So whether or not I actually plugged the number in or I used my double function using my piecewise, we get the same result. Good? Okay, so that is it for these functions. I just want to talk about continuity really quick. And then we are going to have some time to work. Okay, so when looking at all the different types of functions that we will explore this year, there's the idea of continuity. For your AP exam, continuous functions is a big concept, okay? What you need to know for continuous functions, you need to understand the 3 parts of continuity. Okay, so that's in the little sheet, just 2 examples that we'll finish off with. Okay, in your limits package. Okay, so if a function is continuous at a number a, then the limit as x approaches a of my function has to also equal basically the y value at a. That's kind of what this is saying. Okay, so it requires us to check these 3 things. So you'll do these 3 things every single time. 1, f at a has to exist. So it cannot be a restriction or non-permissible value. Okay, if it's a non-permissible value, we already know this function's discontinuous. It has a hole in the graph. Okay. Number 2, we have to check that the limit exists. And trust me, just because f at a exists doesn't mean that the limit exists. If I had a function, let's say, that, I don't know, looked like this, right? This is a function. And even though, let's say this is a, f at a exists here, but the limit doesn't exist at a. That would be an example where the first one works, but the second one doesn't. Okay, and then the third one is that those two values have to equal the same number. Okay, so those are your 3 rules to continuity. You have to know those 3 rules. That is what we'll be checking for. Okay, if any of these 3 doesn't work, then it's not a continuous function. Okay, graphically, we can look at a graph, we can look at the equation, and we can probably see whether it's continuous or not. Like something like this one, like that's a continuous function, okay? But the one on the other side, not a continuous function. But we have to be able to do it algebraically, so showing those 3 steps. So here we have our split function, x squared and x, when x is less than or equal to 0, and when x is greater than 0. Okay, so we're going to check those 3 things. Number 1, does f at 0 exist? Okay, so our a value, and I think I'm missing. Okay, how do I know a is 0? Because this is my potential breakpoint. Okay, one's quadratic and one's linear. There's no restrictions on either one of those. Those individually are both all real numbers. But when I combine it into f of x, that's the only place where it could break. So that's why I'm choosing a is equal to 0, is because that's my break point for this function. Okay, when I plug it in, obviously I need to use x squared because that's the one that includes 0. So I plug my 0 in and I get 0. So f at a exists. So f at a equals 0. Okay, so that's step 1. Step 2, we have to see if the limit exists. Now, remember, my breakpoint is a, and that is equal to the value I want to approach. So my limit as x approaches 0 from the left is going to be x squared. I plug in my 0 squared and I get 0. So the left-hand limit of this function as x approaches a is 0. I do the same thing for the right side, which is x, which is also 0. Because our left hand and our right hand limits equaled 0, the limit existed. Okay, so we got f at a was 0. The limit as x approaches a was also equal to 0, so our third part is actually done. Okay, so if those two are equal to each other, this function is continuous. Okay, if you want to see what it would look like graphically, we have a quadratic for all values less than or equal to 0. Sorry, my smartboard's off. That should not be below the x-axis. Okay, and then my graph is a linear function greater than 0. And so you can see that there's no breaks in this graph. They're connected at 0, 0. Good with that? Okay, let's try one more just to solidify it. Okay, so you have g of x is x squared plus 1 when x is less than 1. And you have x minus 1 when x is greater than or equal to 1. Okay, so step 1, determine what g at 1 is. This time we're going to use the x minus 1 because it's included, and we get 0. Okay, step 2, we're going to check the limit as x approaches 1. So we're going to do the left side and the right side. The left side would be the top, so the x squared plus 1. And the bottom part, the right side, is x minus 1. I plug in my positive 1. I get 1 squared plus 1, which is 2. I plug in my 1, and I get 0. Do I need to even go to the third part of our theorem? Nope, this limit does not exist. Okay, the limit does not exist, so this function is discontinuous. And that's it. That's all you need to know. So for continuity, you just need to check those 3 things. Okay, so I'm going to stop there. I have one more example, but I think I'll do it later. You guys can start working on page 27 in your textbooks. Okay, those questions. So I'll give you guys about a half hour or 45 minutes, then we'll take a break, and then we'll come back and we'll do part 2, which is lesson 1.4. You will find that we're going to go through this stuff really quick, and I know it's super fast-paced, but we have a lot to cover in this course, so there's no slowing down or we'll never get through it.